This presentation is about energy and temperature. A lot of the processes that we'll observe during the semester or learn about involve energy in some way. Some processes will produce energy and others will consume energy. Basically, there's two types of energy. There's kinetic energy and there's potential energy. Potential energy is stored energy, and it depends upon the position of the object, or in this case, the stick figure. Kinetic energy, on the other hand, is energy in motion, and it depends on the mass and velocity of the object. The exact equation is 1/2 mv squared, 1/2 of the mass times the velocity squared. One thing that we need to understand is that all the energy in a system is conserved. We can't gain or lose energy in a system. It's just transferred from one location to another. So in this case, my falling stick man has transferred his kinetic energy to the ground as heat. That's not blood on the ground there. That's supposed to be heat being transferred to the soil particles. And when you heat up those soil particles, they vibrate more quickly. So they have increased their kinetic energy. And temperature is just basically a measure of the kinetic energy of a substance. There are some units of energy that we will use. You're probably familiar with calorie, but it's not the calorie that we use in science. The calorie that we talk about when we talk about food and nutrition is really a kilocalorie. So there are 1,000 science calories in a food calorie. The other standard energy unit that we use is the joule. It seems like a funny unit to use, but it's based on standard metric units. So remember, the kinetic energy was mass times velocity squared. So the unit joule is really kilograms meters squared over seconds squared is the equivalent unit of a joule. So it's based on metric units, where the calorie was just kind of a made-up unit. So 1,000 joules is equal to a kilojoule, and we can relate calories and joules to one another. There are 4.18 joules in a science calorie, a small calorie. One thing that we'll need to do is use some of those relationships to convert data. So sometimes we'll make a measurement in joules or kilojoules, and we'll really want calories. So in this case, I want to convert 253 kilojoules to small science calories, not food calories. So to do this, I'm going to outline some basic information, just like all the problem solving videos that we've done before, where I'm going to list the important data. I know that kilojoules are the same as 1,000 joules, and that 4.18 joules is the same as a calorie. My starting point is my simple measurement. There's only one number stated in the problem here, so that's my starting point. So I've got 253 kilojoules, so I want to get rid of kilojoules, so in the next cell I want kilojoules down in the basement. And I have 1 kilojoule down in the basement and 1,000 joules in the numerator, or the top part of the frame there. So effectively I've canceled out kilojoules, and the unit that survives is joules. I don't want joules, I want calories, and I know that there's a relationship between joules and calories, so I can put the joules on the bottom in the next cell and calories on the top. So I've got 4.18 joules is equal to 1 calorie, and if I just multiply across the top and then divide by the bottom, I should get an answer. The answer I got was 6.05 times 10 to the 4 calories, small science calories. Okay. Sometimes we measure things, or we have data that comes to us in the form of food calories. And remember that food calories are really kilocalories, capital C calories. And I want to find out how many calories Susie was burning when she or how many kilojoules she was burning when she actually burned 500 calories. I don't know if we technically burn it, but we certainly consume that amount of energy. So the only firm piece of data I have there is the 500 calories, and I am going to use the relationship from the previous problem and the further information that 1 big calorie, a food calorie, is 1,000 small calories. So that's my first step, is I'm going to convert into small calories because I know I can relate small calories to joules. And that's my next step, is converting the calories to joules. So now I've got joules, and the problem specifically states that they want the energy in kilojoules. So now I've got to relate my joules to kilojoules. And there we have it. So I've got 1,000 joules equal to a kilojoule. If you just multiply across the top row and then divide by the bottom, you should end up with the correct answer. And here was 2,090 kilojoules. So the last trailing zero was not significant. It looks like all of our data had at least 3 sig figs. I could have written this as 2.09 times 10 to the third kilojoules as well. And that takes us to the end of this presentation. Oops, maybe it isn't. I thought it was the end of the presentation, so sorry about that. Temperature. So the other thing that I forgot that I included on this was temperature. Temperature, as I mentioned earlier, is a measure of kinetic energy. Don't worry about converting between Fahrenheit and Celsius. I can probably count the number of times that I've realistically had to do this on one hand over the last 30 or so years. More often than not, we will, the thermometers that we have are Celsius thermometers, so we'll always measure things in Celsius. We don't have any Fahrenheit thermometers, so there's not really a lot of utility for that. And that's what things like Google are for on your phone. So if you go to a foreign country where they use the Celsius temperature scale, you can use your phone to figure out how many degrees Fahrenheit that is to decide if you need a jacket or if you need shorts and sandals or whatever. But we'll always use Celsius to make our measurements. There's also the absolute temperature scale, and this is relative to a theoretical point of absolute zero. No one's actually made it there, but I think the scientists have made it to within a couple millionths of a degree of absolute zero. Okay, and this absolute temperature scale is related to the Celsius temperature scale as follows. The Kelvin temperature is equal to the Celsius temperature plus 273, or we can look at it from the other end, and the Celsius temperature is equal to the Kelvin temperature minus 273. So if I have a measurement that I've made, in this case in 100 degrees Celsius, and I want to know what that is in terms of Kelvin, it's just a simple formula. I just plug the 100 degrees Celsius, add it to the 273, and I can get my Kelvin temperature. So the other end is a possibility. I know that the boiling point of liquid nitrogen is 77 Kelvin. And if I want to find out the temperature in degrees Celsius, I just subtract 273 from that temperature. So that's a minus 196 degrees Celsius, so that's awfully cold. Things like dry ice, I forget exactly what the temperature is. I think it's like minus 78 degrees Celsius, and you know that you can burn your skin very rapidly if you handle dry ice. So this is even cold dry ice. So this is the real end of the presentation.